So far, we really have only talked about two ways of approaching how we might find the value of a limit. And the two ways that we talked about were numerically. If we use a table, we can fill in the values as x gets close to a certain value and see what happens to y. Well, that is exactly what we did when we talked about this example. This is a numerical way of getting these values, right? As we let x approach values that got really, really close to 2, we found values of y that got really, really close to 4. The other method was graphically. Graphically, we examine the way that the function behaves as x gets close to 4, and we see that the y values tend to agree with the idea that the graph acts like it's going to y equals 4. And that's encapsulated in our limit notation. The third way that we're going to get used to is analytically. Now, essentially, we can say for right now that if a function is a well-behaved, if f of x is well-behaved, I'm going to put that in quotes, well-behaved, because we're going to have to figure out what that means. If it's well-behaved, that is, if it's the kind of function that doesn't do like weird stuff as x gets close to a certain value, then we could say then that usually we treat it this way, that it is the kind of limit that as x approaches c of f of x, then hopefully the limit will equal f of c. That is, it'll be the same, the function will act exactly like it is at that point. That's not always the case, right? We saw that, you know, sometimes it is, sometimes it isn't, right? In the case of the limit as x approached 4 for the function 0.5x plus 1, we got exactly the same value as if we took 0.5 times 4 plus 1, which is to say we got our limit of 3. On the other hand, right, so y equals 0.5x plus 1 is an example of a well-behaved function. On the other hand, when we looked at our limit as x approached 2 of x squared minus 4 divided by x minus 2, right, we saw that this was not the same as saying 2 squared minus 4 divided by 2 minus 2, right? Right, that's 0 over 0, which is indeterminate. We definitely could, based on both the graph and the numbers, we saw that the limit approaches 4, right? So the question was, how did we rectify these two? Well, that's one of the techniques that we're going to learn in the next section. How do we actually do that? For right now, we're going to stick with the fact that we can deal with it this way. There are some cases where a limit will fail to exist. For example, if we have a certain function that approaches different values from the left and the right, say we have a piecewise function that does weird things. Let's talk about one. Let's say we have a function that looks like this, all the way up to x equals 4. But at x equals 4, all of a sudden it changes behavior and it does something weird like this, right? If we say f of x is the kind of function that does this kind of thing, well, what's happening is that as we approach 4 from the right, we're getting a different value as f of x approaches from the right, so from the left. So we say that this function, the limit as x approaches 4, in this particular case of f of x, fails to exist. Usually we write DNE, where DNE stands for does not exist. And that's always a possibility depending on the way the function is defined. Another case is that sometimes we have functions that go towards infinity or negative infinity. And don't forget, we had those kind of functions when we were talking about rational functions. And in our rational functions, we determined that sometimes we get a feature called a vertical asymptote, even if there's a horizontal asymptote or not, right? And if we have a vertical and horizontal asymptote, we could have the kind of function that as x approaches 5, like in this case, y tends towards infinity, or y tends towards negative infinity, right? This is going to be that unbounded behavior. Finally, one other kind of behavior where we know the function's not going to limit is not going to exist is when it oscillates between two different values. And we'll find that there are these kind of functions. We'll probably won't see them in this chapter yet, but if we had the kind of function that oscillated between two values, and let's say it started oscillating much closer, and as we got closer and closer to 7, let's say the oscillations got really, really close, and then all of a sudden, boom, they stopped really getting closer at all. They just kept oscillating between two values like this, even if the function was or was not defined here at 7, right? We would say that this is the kind of function where the limit does not exist. So the limit as x approaches 7 here of f of x does not exist in this case. So those are the three situations that we're going to have to look out for, and as we get closer to it, we'll find out how that works.